So, dear students, I welcome you to the fourth unit of electromagnetic field subject, which is time varying fields and Maxwell's equation. I am Sudarsanam, Assistant Professor in the Department of ECE, R.M.K College of Engineering and Technology. So, to give you a short overview of what we have studied already, in the unit 1 you studied the various vector, how to solve, to different vectors, adding, subtracting, projection. So we studied Stokes theorem, divergence theorem, the different coordinate systems, and writing formulas for different coordinate systems. The second unit is electrostatics. In electrostatics, we assumed that there is a charge which is kept stationary, which is not moving. For that electrostatic charge, what is the electric field? Okay, with the help of Coulomb's law and Gauss law, we found out what is the electric field intensity for a finite line, for a charge of finite line with uniform charges, and for an infinite line, for a circular sheet, for an infinite sheet. And also by using Gauss law, we also calculated what is electric field intensity. And then in the third unit, we studied magnetostatics. Magnetostatics spoke about what is magnetostatics. In a current, whenever a current flows through a conductor, magnetic field is set up. So in magnetostatics, we assume that the current which is flowing through the conductor is a steady current, a DC current, which is not varying with respect to time. So since it is a steady current flowing, the magnetic field which is set up due to that steady current, the nature of the current is not varying with respect to time. The magnetic field is also not varying with respect to time. A stationary magnetic field was set up around the conductor. So for this, for different geometries, for a finite line, for an infinite line, for a circular loop which is placed along XY plane. So when a circular loop is placed carrying steady current I, which is placed on the XY plane, on the positive z, a point somewhere along the z-axis, positive z-axis, also the negative z-axis, and also in between, in the axis of the loop, we calculated what is the magnetic field intensity. So also we made use of the Ampere circuital law. And in magnetostatics, we studied about the inductive principle, inductive energy. Since this is magnetostatics, so we studied this. And in the electrostatics, we also studied about the capacitive nature, capacitance of that. So now we are introducing to you time varying fields. Unit 4 is time varying fields, where the nature of the supply is time varying in nature. A time varying field is given to a circuit. So the parameters electric field and magnetic field here will also be time varying in nature, and that we are going to see here in the fourth unit. So Maxwell's equations is the equation which really helps us in that. So here the short video, I have planned to give this as a two short videos of 10 minutes approximately, of that length, to just to explain some of the important concepts in the fourth unit. So the overview of the Maxwell's equation, continuity current equation of continuity current, Faraday's law, displacement current, Maxwell's equation, we'll see one by one. So this is James Clerk Maxwell, the man who was responsible for a very important invention. Okay, James Clerk Maxwell was a Scottish mathematician and a scientist. So he was the person who was responsible for the classical theory of electromagnetic radiation, and he also found out that electricity, magnetism, and light, these three are different manifestations of the same phenomenon. He found out that these three, electricity, magnetism, and light, they have something in common. They are the same. So he gave 4 sets of equations which we would be deriving in this unit, which are very much they have survived. So he invented these equations. He gave these equations in the 19th century. Now after 2 centuries after the invention or the postulation of the theory, still these 4 theories are holding good, and many of they have survived the test of time unblemished, without any errors. with these four basic equations, with the assumptions which are made in these four equations, all of the theories are being built, and they have, for so far they have been unrivaled. You know, they have, with the help of these equations, some theoretical and experimentations were all done by James Clerk Maxwell. Thanks to James Clerk Maxwell for his four inventions, for the inventions of these four equations that he has given, which we can see here. So these are the four different equations of Maxwell's equations. So these four equations were derived from few laws. So you can see it in the left hand side, the name of the law: Gauss law, Faraday's law, Gauss law for magnetics, also Ampere's law. With the help of these laws, these equations were with these the basic findings of these equations, Maxwell had derived these four sets of equations. So first I'll take you through the Faraday's law. What is Faraday's law? Faraday's law states that whenever an AC current is given, so in a circuit here you have an inductance is here. What will be the voltage across the inductance? The voltage across the inductance will be minus N into d phi by dt. The induced voltage across the inductance will be minus N into d phi by dt. So phi is the magnetic flux which is created in the inductance. What is N? N tells you about the number of turns, number of windings, turns in the inductor, and the minus sign, it tells you about Lenz's law. What is Lenz's law? The polarity of the induced EMF will be such that it opposes the change of the magnetic flux. So the minus sign is given here. So the induced EMF will be opposing the magnetic field which is given here. So the minus sign is given there. So this is Faraday's law. So with the help of Faraday's law, we are going to derive Maxwell's second equation. We will see how it is being derived. V is equal to minus dou phi by dou t, d phi by dt, or dou phi by, okay, V is induced EMF V is equal to minus d phi by dt is given here. So minus N into d phi by dt also you can write depending upon the number of turns. So now let's take here, you are seeing here a stationary loop is given here. See, you see a loop in which a time varying current field is given. So the current which is flowing here, the loop is not at all going to move, it is going to be as such. The current which is flowing through the conductor or through the loop is time varying in nature. So when current flows through a conductor, magnetic field will be set up 90 degrees to it, which you already know. Okay, so that is already given, that is also given here, but the magnetic field here is going to be time varying. First we will write what is V EMF is equal to line integral E dot dl. This is the relationship between voltage and the electric field intensity, which you have seen in the second unit. We will make use of that equation, and also in the second equation is phi is equal to surface integral B dot ds. What is this B dot ds? This is a relation. What is phi? Phi is magnetic flux. What is V? Magnetic flux density. The relationship between magnetic flux density and magnetic flux is given here as this equation. So now we'll substitute in the left hand side of the equation VMF. I'm going to write it as line integral E dot dl, and instead of this phi minus d phi by d phi, I'm going to substitute as integral d b ds. So this differentiation term will be there. So this d by dt, when it goes inside the integral, it becomes dou b divided by dou t. So here I'm going to this equation 4.7, which is V EMF is equal to line into closed loop integral E dot dl is equal to minus surface integral dou b divided by dou t ds. Here in the left hand side of the equation I have line integral E dot dl. With the help of Stokes theorem, I'm going to write what is Stokes theorem. Any field, you can write that field as a closed contour. You can you calculate for a closed contour, it becomes a surface, right? It equates a line integral and a surface integral. So line integral E dot dl will become surface integral del cross E ds. You will take the curl for the field. So E vector is written as del cross E ds. So this is a change that we have done. Now both in the equation 4.8, you see del cross E ds is equal to minus dou b divided by dou t ds. So you can cancel these integration and you can write it in the form of a point form of Maxwell's equation is del cross E is equal to minus dou b divided by dou t. This is Maxwell's second equation. Next we'll move on to the continuity current equation or continuity equation. This is a very important concept in deriving Maxwell's first equation. What is continuity equation or continuity current equation? So let's imagine a small a small cuboid. Okay, imagine a cuboid. Inside the cuboid there are stationary charges, so they are not moving, like as if you will be having a lot of balls inside that small box. So there are charges inside the box as shown here. So the box has how many sides? 6 sides. So initially the charges are not moving. After some time, when the current is starting to flow, that means that charges are starting to move in 6 different directions. That is shown in the figure here. So the charges which were stationary inside the box starting to move in 6 different directions is shown here. So that is given by the equation minus dq by dt, or del q divided by dt, is equal to I out, net current flowing out. So net current flowing out can be minus dq by dt. What is it? Minus. Why do I write minus there? Because in that small in the small area from where the charges are concentrated, they are going to move out of that small box as current is starting to, the charges are starting to move. So concentrated charges are going to move in six different directions. They are going to move. So it becomes a volume, and since it is, the charges are coming out of the volume, the magnitude is going to become less and less. So I'm going to introduce that minus sign is given there as because of that. So minus volume integral dou d rho v divided by dou t dv. We are equating it as, you are writing for that volume, 6 sides, no? So volume, we are equating it. Current and current density can be equated as I is equal to surface integral j dot ds. Now in the right hand side, by making use of divergence theorem, j dot ds can be written as del dot j dv. So divergence theorem relates surface integral volume integral. J dot ds can be written as volume integral del dot j ds. So when you equate these two terms, you can write del dot j is equal to minus rho dv by dot. What is j? J is current density. What is rho v? Rho v is volume charge density coming out of the volume. The minus sign tells that minus. Why do we write minus? Because the charges are coming out, so we are writing it as minus dou rho v by dou t. We can also write this. This is a very important continuity current equation. We can also write this equation as del dot j plus dou rho v divided by dou t is equal to 0. So let me stop this first video, and I'll start to explain to you the rest of the terms in the second video. Thank you.